Hello my friends, and welcome back to the You Can Do TV channel. The Brenner Base Tunnel is a significant railway tunnel project in Austria, connecting Italy from Innsbruck to Franzensfeste. Spanning a length of 55 kilometers, it includes the Innsbruck bypass. As the longest underground railway link globally, the tunnel is divided into 4 sections through multifunction points, accessible from external access tunnels. The construction process of the Brenner Base Tunnel involves several phases. Initially, a promontory emerged, and various access tunnels were established, followed by the creation of the 2 single-lane main tunnel tubes. The project is designed to have the longest underground railway connection, anticipated to become operational in 2026. The expansion of the railway axis across the Brenner region holds significant importance for the European Union. It is envisioned as a vital project for fostering modern rail connections between Berlin and Palermo, catering to the needs of future decades. The Brenner Base Tunnel serves as the core of this new high-performance route, also referred to as Axis 10. During the initial construction phase, an exploratory tunnel is built beneath the 2 main tubes, with particular emphasis on geological exploration. After each blast, a detailed inventory is created, and rock samples are periodically taken to ensure safety during tunnel construction. The exploratory tunnel serves multiple purposes during the propulsion of the main tunnels. It facilitates drainage of mountain waters and material transport. Additionally, the access tunnels play a crucial role in tunnel ventilation and operation. Since April 2011, construction work for the Brenner Base Tunnel has been underway. Various drives are being carried out in parallel, including the Palace Tunnel, Random Tunnel Wolf, and Saxony. Breakthroughs in tunneling milestones have been celebrated, and careful monitoring of the environmental impact and water balance is conducted. The tunneling work continues to progress smoothly, with all 4 construction sites in North Tyrol operating at full capacity. Access tunnels in both North and South Tyrol are either completed or about to commence. The exploratory tunnel crosses the Peri-Adriatic Seam, a fault line in the Earth's crust running through the Alps. Cutting-edge techniques, including tunnel boring machines and concrete skills, are employed for expanding the tunnel's cross-section. The Brenner Base Tunnel is a monumental and prestigious construction endeavor that attracts significant interest from various sectors. Open tunnel events draw thousands of interested individuals seeking insights into the project's progress and the remarkable engineering feat that is the Brenner Base Tunnel. The Red Line North Underground is an integral component of Qatar's ambitious National Development Plan for 2030. Known as the Qatar National Vision 2030. Spanning around 13 kilometers, this underground transportation marvel extends northward from Musharraf Station and comprises 7 modern subterranean stations. The project involved the creation of dual parallel tunnels, each approximately 11.6 kilometers in length, boasting an internal diameter of approximately 6.17 meters. This innovative infrastructure initiative is part of a larger scheme, including 3 additional metro lines, all designed to enhance Qatar's mobility landscape. The Red Line North Underground project showcases Qatar's commitment to advancing its transportation infrastructure in line with its visionary development goals. The Peljasak Bridge in Croatia spans a length of 2,440 meters, incorporating approach spans. This extradosed cable-stayed bridge stands adorned with 6 towers, each boasting a single central cable plane, and it proudly presents 5 main spans stretching over 285 meters each. A network of 10 supports stands steadfast in the water, accompanied by 2 imposing piers anchoring the bridge to the land. Once the interlinking roadways are fully realized, vehicles will traverse the waters, bridging the Croatian mainland with the previously isolated Dubrovnik. The foundation of this monumental structure is rooted in the fabrication of 150 straight welded tubular steel piles, ranging in design lengths from 36 meters to an impressive 130.6 meters, with a diameter of 2 meters. These piles lay the groundwork for the bridge's stability. Remarkably, more than 70% of these piles exceed a design length of 100 meters. Composed of S355NH with a 40 mm wall thickness, the pile body is paired with 2-meter-long pile shoes from S60NH, featuring a 60 mm thickness. An instrumental participant in this endeavor was the colossal pile-driving barge, measuring 78 meters by 36 meters by 128 meters. This maritime behemoth sported a draft depth of 4.2 meters and a displacement tonnage of 12,000 tons. Notably, it held the prestigious title of the world's largest pile-driving barge at the time of its employment. With the capacity to drive piles of up to 7 meters in diameter and 500 tons in weight, this vessel played a crucial role in securing the foundation of the bridge. The bridge's superstructure adheres to the conventional box girder design, featuring a 3-cell box donning a 22.5-meter width and a robust 4.5-meter thick orthotropic deck plate. The assembly of this superstructure was a nuanced process involving the creation of 165 distinct segments, each tailored to specific erection methods essential for on-site installation. In constructing the main span, the balanced cantilever method was employed. This intricate process entailed installing 12-meter-long segments in a precisely orchestrated sequence. Meanwhile, the installation of 10 pairs of girders for each of the 6 pylons was facilitated by flat barges, maneuvering beneath derrick cranes that hoisted them into place. Efficiency was paramount in erecting the bridge's 6 side spans, amounting to a cumulative length of 657.6 meters. To expedite this stage and minimize on-site welding, extra-long segments ranging from 36 to 56 meters were crafted. These elongated segments, weighing up to 1,000 tons, were deftly positioned into place by a floating crane with a 1,000-ton capacity. The on-land portion of the bridge relied on 12-meter-long curved and straight sections, which were elevated using a floating crane onto temporary onshore platforms. Hydraulic jacks and skid tracks facilitated their final placement. Completing the superstructure entailed the fabrication and installation of 7 closure segments. The segments, varying in length, were artfully integrated using derrick cranes. The crowning achievement was marked by the successful completion of the 6 concrete pylons, paving the way for the installation of the 12-meter segments constituting the main spans. Ultimately, on July 29, 2021, the last closure segment was raised and welded. The Lake Mead third intake project secures southern Nevada's water supply in the midst of a severe drought and the onset of climate change. As Lake Mead's water levels dwindled, threatening vital water access, this project took shape. The endeavor involved excavating a 600-foot deep shaft, navigating a tunnel boring machine through challenging rock conditions, and constructing an innovative intake structure offshore. Overcoming hurdles of high pressure, unstable geology, and unexpected inflows, the project's completion ensured a reliable water source for Las Vegas and surrounding areas. The excavation of the shaft to create a passageway for the intake tunnel. The process commenced with exhaustive planning and preparation. Engineers analyzed geological data and ground conditions to determine the optimal location and dimensions of the shaft. A comprehensive understanding of the surrounding rock formations, water tables, and potential obstacles was essential to ensure a safe and effective excavation. Drilling operations. Drilling marked the initial step in creating the shaft. Powerful drilling rigs were employed to bore holes into the rock face. These strategically placed holes would serve as entry points for the subsequent steps of the excavation process. Precision drilling was imperative to ensure the shaft's alignment and stability. Dynamite charges and controlled blasting. Once the boreholes were in place, dynamite charges were carefully inserted. These charges were strategically positioned to induce controlled blasting and fracture the rock layers. The blasting process was meticulously coordinated to prevent excessive damage while effectively breaking down the rock into manageable fragments. Fragmentation and debris removal. The controlled explosions resulted in fractured rock segments. This fragmentation was crucial for two reasons. It facilitated the removal of debris and created a pathway for subsequent excavation stages. Specialized equipment, including buckets and conveyors, was employed to lift the fragmented rock to the surface, ensuring a continuous flow of debris removal. Challenges and adaptations. The excavation process was not without challenges. Unpredictable geological conditions, potential water ingress, and the need for constant stability evaluations demanded adaptability. The project teams showcased their expertise by making real-time decisions to ensure the safety of both the construction and personnel. Precision and safety. Precision was a constant focus during the excavation. The accurate placement of boreholes, controlled initiation of dynamite charges, and efficient removal of debris were all integral to the success of this phase. Moreover, the safety of workers remained paramount, with stringent protocols in place to safeguard them during drilling, blasting, and debris removal. Operating in an aquatic environment added a unique layer of complexity to the construction process. Marine crews were tasked with excavating a deep hole in the lake bed to accommodate the intake structure. This required navigating the unpredictable waters of Lake Mead, contending with variable weather conditions, and managing strong winds that created rough seas. Marine operations also encompassed the delicate task of lowering the intake structure into the lake, a feat that demanded precision and coordination. The structure, suspended from a barge, was gradually submerged and secured to the lakebed floor using an intricate system of cables and jacks. This underwater ballet required the expertise of divers and remotely operated vehicles, ROVs, to ensure the structure's proper placement and alignment. Concrete ring segments played as the protective lining for the newly excavated tunnel. These meticulously manufactured segments formed a robust, watertight seal that ensured the tunnel's stability under the lake's immense hydrostatic pressure. Precision was paramount in the creation of these segments. Engineers adhered to tight tolerances, ensuring that each segment fits seamlessly with the next to create a continuous and secure tunnel liner. The segments were designed to withstand the pressure exerted by the surrounding water, safeguarding the passage and workers with. This innovative solution showcased the marriage of engineering knowledge and advanced materials to meet the unique challenges posed by the project's underground environment. The tunnel boring machine, TBM, operates like a massive mechanical worm to methodically excavate tunnels. Equipped with a rotating cutting head studded with disc cutters, the TBM gradually bores through rock and soil, breaking it into manageable fragments. As it advances, hydraulic jacks push against tunnel walls, providing stability. The TBM also creates the tunnel lining concurrently, placing concrete segments to form a secure, watertight structure. Workers in the control cabin oversee its progress, adjusting parameters as needed. The TBM significantly reduces the environmental impact by minimizing surface disruptions and expediting construction. The TBM operator's job was multifaceted and demanding. They closely monitored the machine's performance, keeping a watchful eye on parameters such as pressures, alignment, and the cutter head's progress. This required quick thinking and adaptation to varying ground conditions and pressures. The operator's ability to interpret real-time data from the machine's sensors was crucial in avoiding potential hazards and ensuring that the tunneling proceeded smoothly. Constructing the intake structure for the Lake Mead third intake project was a monumental endeavor that took place both onshore and offshore. This structure would play a vital role in drawing water from the depths of Lake Mead to supply southern Nevada. The process began with meticulous planning and fabrication. On the offshore front, marine crews worked tirelessly to assemble the intake structure on a barge. This structure, weighing over 1,400 tons and towering more than 90 feet, was designed to withstand the immense pressure of the lake's depths. Cables attached to each corner allowed for precise control as the structure was lowered into the water, ready for its final placement. Braving the elements, including high winds and choppy waters, the marine crews successfully maneuvered the barge and the intake structure to the designated location. Once in position, the structure was methodically submerged into the lake, a remarkable feat that required synchronized efforts and precise calculations. This submersion was a critical step in securing a stable foundation for the intake. Simultaneously, onshore operations were in motion to provide the essential building blocks of the project. The concrete ring segments. These segments formed the tunnel liner that would ensure the stability of the intake tunnel, even under the intense pressure of Lake Mead. Manufacturing these segments to exact specifications was essential, as they needed to fit seamlessly and create a watertight seal. The delivery of these concrete ring segments was a carefully orchestrated process. Each segment was cast with precision, adhering to strict tolerances to guarantee a secure fit within the tunnel. These segments were then transported to the construction site, ready for installation. Coordinating the delivery of the segments with the progress of the tunnel boring machine, TBM, was a critical challenge. The segments needed to be in place as the TBM advanced, ensuring that the tunnel liner was established in a timely manner. The segments were lowered into the tunnel, positioned by workers, and meticulously aligned to create a continuous and secure passage. The construction of the bridge to Russky Island over the eastern Bosphorus Strait marks a significant milestone in the development of Vladivostok. Soaring 70 meters above the water level, the central span of the bridge stretches over 1,100 meters, setting a world record. The pylons supporting this grand structure rise to a towering height of 320 meters, and the mainstay cables extend an astonishing 580 meters. One of the remarkable aspects of this project is its remarkable speed. The bridge is being erected in a record short time of 43 months, an impressive achievement given the complexity and scale of the endeavor. Vladivostok, often hailed as the largest Pacific port in Russia, demands a bridge that can accommodate vessels of all classes. Spanning about 1.5 kilometers in width over the eastern Bosphorus Strait, the bridge faces challenging weather conditions. In the project area, wind speeds can reach up to 36 meters per second, while storm waves can surge to 6 meters in height. The region experiences diverse climatic conditions, with winter temperatures plummeting below -30 degrees Celsius and summer temperatures soaring to 37 degrees Celsius above zero. The construction site was equipped with a comprehensive array of specialized equipment, including over 320 pieces of machinery. Innovations were introduced, such as reverse circulation drilling rigs used for the first time in Russia for bridge construction. These advancements, including the powerful Bauer BG-40 drilling rig, facilitated the construction process. The erection of the bridge commenced with the construction of the viaduct, measuring over 900 meters in length. This viaduct would serve as the foundational structure upon which the entirety of the bridge would emerge. The viaduct's piers, ranging in height from 9 to 30 meters, were meticulously conceived to seamlessly harmonize with the unique soil conditions present in the construction area. Central to the stability and durability of the viaduct were the bridge's piers, and their design was adapted to accommodate the varying depths of the underlying soil. These piers, each a vital element in the bridge's support system, featured cast-in-place grillage piles spanning from 5 to 20 meters in length. The dynamic nature of the soil necessitated a flexible approach, ensuring that each pier's foundation could respond adeptly to the specific soil conditions encountered. As the construction progressed, the challenge shifted to the complex task of erecting the pylons that would eventually support the cable-stayed span's stiffening girder. The pylons, towering at an approximate height of 35 meters, played a pivotal role as load-bearing structures, responsible for the intricate transfer of forces within the bridge's framework. To navigate the intricacies of pylon construction, a tailored solution was introduced in the form of custom-made self-climbing formwork. This innovation streamlined the process of concreting the pylons, ensuring precision and efficiency in every phase of construction. By integrating this advanced formwork system, the construction team was able to achieve remarkable progress, optimizing both time and resources while maintaining an unwavering focus on quality. An equally significant advancement came in the form of utilizing self-compacting concrete, a material designed to optimize both the placement process and the overall quality of the final reinforced concrete structure. This innovative concrete mix was engineered to possess a unique blend of flowability and self-leveling properties, allowing it to effectively fill intricate spaces within the formwork without the need for external vibration. This not only expedited the concreting process, but also enhanced the uniform distribution of concrete within the formwork, leading to greater structural integrity. The implementation of self-compacting concrete also contributed to reducing the potential for air voids and imperfections within the concrete, resulting in a more durable and resilient structure. This material innovation not only increased the efficiency of construction, but also underscored the project's commitment to embracing cutting-edge solutions for enhanced outcomes. Board piles and enclosing sheeting were put in place, and drilling and pile concreting operations were conducted from the water at sea for the first time in bridge building in Russia. A total of 120 board piles, each 2 meters in diameter, were installed to build the footing of each pylon on Russky Island. These piles are permanent metal casing parts. The piles were bored to a depth of up to 77 meters. On the Nazim Open Insula, the rock is closer to the ground surface on the island side, so the piles of the M7 pylon footing are 40 meters deep. A self-compacting concrete mix based on sulfate-resistant Portland cement was used for the pylon footing concrete, protecting it against erosion and preventing rebar rusting. The highly flowable concrete mix was placed continuously for several days in 10 to 15 centimeter layers. Custom-made concrete pouring pipes were utilized to prevent separation. Strain gauges were installed in the pylon village to transmit data on stress conditions. These gauges ensure the evaluation of structural conditions during erection and later in operation. The pylons have a varying cross-section that tapers upwards. The bottom part of the pylons carries the maximum load, so heavier reinforcement is provided in that section. High-grade concrete with higher density than ordinary concrete is used. Custom-made self-climbing formwork is employed to concrete the pylons in 4.5-meter-high sections. This formwork significantly reduces the erection time of the cast-in-place reinforced concrete structure. The cable-stayed span structure is designed with an aerodynamic profile to withstand squally wind loads. The bridge model underwent wind tunnel testing. The navigation span's stiffening girder is all metal and designed as a box, including top and bottom orthotropic plates, crossbeams, and diaphragms. The 103 panels, each 12 to 24 meters long, are pre-assembled off-site and then transported for installation. The continuous spans are made of pre-stressed reinforced concrete with additional plastic ducts for high-tensile pre-stressing steel bundles. These bundles are tensioned at 350 tons after concreting. Stay cable supports, made of low-alloy steel pipes with anchor bases, are installed in parallel with reinforcement work. A compact cable configuration reduces wind loads and material costs. The cables consist of strands, each about 16 millimeters in diameter, composed of galvanized steel wire. The protective cable jacket is made of high-pressure polyethylene, ensuring a design service life of at least 100 years. The bridge construction project attracts visitors, government commissions, foreign delegations, and journalists every month. The temporary Vista platform will be transformed into a permanent structure, making the bridge a major landmark in Vladivostok and a symbol of the construction company. The recently constructed Genoa Bridge stands as a remarkable feat of engineering, boasting an impressive length of 1,067 meters, divided into 19 spans. This bridge holds immense significance as a pivotal node in Italy's transportation infrastructure, designed to shoulder the bustling traffic of the city, which stands as a key European hub. The backbone of this structure comprises 18 massive, elliptically shaped, reinforced concrete pillars. These pillars serve as the sturdy foundation for the bridge's metallic framework, a testament to meticulous engineering. As it stands today, the bridge is in the midst of its anchoring process, firmly embedding itself into the bedrock of the terrain. Positioned on the Campasso slope on the eastern side of Valpolsevera, these columns soar approximately 37 meters high, with the tallest pillars surpassing an impressive 80 meters. This towering presence is reminiscent of a towering 30-story skyscraper. The construction's exceptional demand necessitated the swift erection of 18 of these colossal pillars, a feat accomplished with remarkable organizational precision. The lifting of these pillars owes its success to innovative structures known as casseri rampani. These structures rise in tandem with the elevation of the pillars, simplifying the otherwise complex process. During the construction phases, intricate cages of reinforcing steel are hoisted and meticulously positioned. These cages are then secured together, enclosed within the casseri framework, imparting the geometric integrity essential for the bridge's strength. The workforce comprises specialized teams of 5 to 7 workers, adept at handling tasks at considerable heights. The concrete formulation used in the pillar creation is meticulously calibrated, tailored to deliver optimal strength, durability, and aesthetic appeal. Notably, the aesthetic qualities of the concrete are achieved through a carefully curated blend of aggregates, including gravel and sand, selected from a single quarry to ensure a consistent and almost marble-like appearance. Each pillar's completion is marked by the placement of metallic span support elements called apogee. These elements are positioned atop the pillar's distinctive features, symbolizing the successful integration of the pillar into the larger bridge structure. Despite its imposing scale, The bridge boasts a curvilinear and seemingly weightless design that defies its monumental role. The construction site, a hive of activity, witnesses the synchronous efforts of numerous companies, striving to achieve the delicate equilibrium between urgency, structural integrity, and aesthetic finesse. Their aim is to reinfuse Genoa with the vibrant dynamism that has long defined the city. Working 24/7, activities progressed rapidly, and within a little over 8 months, the bridge's piles were completed. A truly remarkable feat. As the piles grew, the assembly of metal decks started on the ground. These decks were then delicately lifted and positioned onto the piles through meticulous launching operations. The completed metal decks, once elevated, were then connected to adjacent ones, forming a single massive steel beam stretching 1,067 meters. This rebuilding effort is a reaction to the disaster, a key infrastructure for the city and European connections being reconstructed to re-establish trust with citizens. The Genoa model, developed over months of negotiation, brings together private companies and public institutions for efficient, continuous, and uncompromising work. The new Genoa Bridge stretches 1,067 meters, built with 67,000 cubic meters of concrete and nearly 25,000 tons of steel. The collaborative effort of over 330 Italian companies and over 1,000 workers across 40 trades brings this project to life, employing innovative techniques like steel cables for lifting massive segments. The bridge is a marvel of sustainability, technology, and innovation, with its discreet design blending with the Mediterranean wind and solar panels absorbing sunlight. This venture stands as a testament to teamwork, collaboration, and the potential for remarkable achievements when will and cooperation align. On August 3rd, the inauguration of the Genoa-San Giorgio Bridge took place. Less than 2 years have passed since the collapse of the Morandi Bridge, and in under 12 months since the foundation of its first pillar, the entire bridge was raised.